What I'll do is, I'll just go through what you did yesterday, class quiz, but slightly differently. Okay. Uh, let's think about how we can visualize shear. Okay. So that'll give an idea of how do I intuitively understand the shear flow and all those. Okay. So since you have already done shear, I'm going to ask you this question. Okay, so let's say I have a circular cross section. Okay, and it's a thin cross section. Okay, what do you mean by thin? The radius or the diameter is very high compared to the thickness T. Yeah. Now, if this shaft, let's say this is a shaft, is subjected to torsion, right, or a torque, this would the torque would induce what? The shear stresses, right? And we have drawn the shear stress. In this case, the shear stress will be like this, right? I can draw it like this. This is the shear stress that I'm representing, right? One thing good about this is the thickness is very small, right? And therefore, the variation of tau from here to here, okay, can be assumed to be minimum, right? So which means that I can assume that there is constant shear stress over the thickness. All right. Are you with me here? This is simple and clear, right? And therefore, I'm able to draw this shear stress. Okay. Let's do one small exercise and find out what we obtain from a simple free body diagram. So what I'm going to do is I'm going to just cut off a small portion here. Okay. Let me take it as like this. Ah, maybe here it's easier this way. Okay, I'll take it like this. So I'm going to take a section like this. Okay. Let me draw the section over here. Is this visible? This side or this side? Let me put off the light. One second. Sandeep, this is better. Is it visible?
Yes, sir. Yes, sir.
Okay. So let's draw the small section that we have taken. Okay. I'm going to take this as some small length. So as I go traverse, this length is, let's say, delta S. Delta S. Okay, so I'm taking a small elemental length, and this is dx, correct? Right? So why am I taking it as dx? This direction is x direction. Okay. So I'm going to draw this. When I do this, there is shear over here, right? Which means on the other side also I should have shear, right? And this is, let's say, tau. Okay. Now I don't know whether this tau is going to be constant throughout. So what I'll do is I'll take this as, let's say, tau, which is at an s, which is s is nothing but a parametric, let's say, coordinate s, right? And this is tau plus delta tau, right? Just like what we did in most of the elemental calculations, right? Over and above that, let's also do something more. Okay, and that is this. Let's say this is the thickness T, and I'm going to assume that the thickness is also varying with the coordinate. Okay, for example, I can take the thickness to be varying like this. Like this, you can see that this thickness is more, this thickness is less, right? So I can vary the thickness also here. So which means that I can take the thickness over here as T, and the thickness over here is T plus delta T. Are you okay? Right? This is tau at S plus delta S, and this is tau at S. This is thickness at S, and this is thickness at S plus delta S. Okay, so another way of writing this is tau of S plus delta S, and this is T of S plus delta S. What I have done is practically expanded this and used truncation, saying that only the first term is available. So far, okay? Is this clear? Any questions? Yeah. And what would be this tau and this delta T? I can take tau to be varying with respect to this in a continuous way, and therefore I can take this to be dou tau by dou S delta S. Yeah, can I not? Can I not do this? In a similar way, I can take delta T to be varying with respect to S like this, so that I can write this completely in terms of S. So far, okay. So what we have drawn is this. So mind you that there is a shear stress that I've shown over here. So I have to show a shear stress here. This is the shear stress that we are talking about. This could be varying from tau S here to tau S plus delta S here. Okay. If this is clear to you, then we can go ahead, derive using a simple free body diagram principle, where remember this direction is the x direction, right? We have the shaft that is running like this. This is the x direction. This is the x direction, right? And I seek to find out the equilibrium in the x direction. Okay. All right. So far, okay. Can you quickly on your notebook write down what this would give? What this would give? Quickly. What would sigma f of x give you? Well, here there are only two forces that are taking part, which is due to this tau s, and which is due to this tau plus delta at s plus, or tau at s plus delta s, right? So I can now write this to be equal to, help me out, help me out, help me out. This is the direction like this. This is minus, this is plus, right? So it is tau plus delta tau. This is the shear stress. I need to multiply by the thickness, which is T plus delta T minus tau times T, right? I'm missing something here, which is what? What am I missing? Delta X. This happens to be the area. This happens to be the area. Multiplied by the stress will give me the force. This is the other force, right? This is what I get, right? And I can expand this and write it down. What do I get? Tau T will go away, right? So this will get cancelled. Somebody is unmuted. Can you please mute? Sandeep, can you mute everybody?
Yes, sir.
Thank you. Thank you. Now,
Sir, you're on. You're muted.
So if I expand this, what should I get? Okay, this is equal to 0, right? Right? If I expand this, what should I get? If I expand this, what should I get? I have a t that is multiplied by delta t. I have a tau that is multiplied by delta t. Correct? So I should get what? One of you? Somebody has written del t. Yeah, exactly. Exactly. So dou tau by dou s times t plus dou t by dou s times tau. This is equal to 0, no? This looks familiar. Of course, this is same s. S is the only single variable. I can also write this as dt by ds here. This looks something that is simple. Why not cancel delta x? Yeah, I can cancel delta x. Yeah, you're right. Delta x I can cancel. What is this? What is this? Dou by dou s of what? Tau s. Tau times t. Right? And what is this equal to? 0. If tau times t equal to 0, what do I conclude? Tau times t is equal to 0. Automatically that tau t is a constant. Okay, so what do I get? Tau times t equals a constant. What do I mean by that? In this, if I take any point, any s along this, so this is the s, if I take any point, I know that tau times t is a constant. Okay. This looks very familiar. I'm going to put this equal to q so that you get an idea of something that you're doing in fluid mechanics. Let's say this is a channel or a pipe. Okay. So it is a pipe that is going around like this. What do you know about the flow here? If it is a fluid flow, what will be a constant? What will be a constant?
Rho will be a constant, sir.
Flow will be a constant, which means this q is equal to a constant. So I'm getting some kind of analogy, and that's one of the reasons why we call this as shear flow. Okay, where we attempt to use this in order to intuitively understand what is happening to it. Okay, so far okay. Let's go to the next one. So let me take the same thing. Now I need to find out torque T, right? That has to be a resultant of the shear stresses that are acting here, right? Are you with me? So for example, if I take a small elemental length delta S here, right? And the shear is acting over like this, right? And let's say this is the, I'm going to make it bigger so that it's possible for you to see, okay? So let me take it like this. Let's say I cut this way and I cut like this, okay? And let's say this is the shear stress, right? This is about which I'm finding out the moment, all right? So that I can find out torque. So what is torque equal to? Torque equal to this distance is ds, right? Go ahead, tell me. Thickness is known to me. what should I get? What should I get? Let's say this radius is r. I need to find out torque because the external torque should be equal to the internal twisting moment, right? So the twisting moment that I can write over here should be equal to, help me out, please. Help me out. I'm just going to do it for this and integrate it over the entire circle. Okay. So what would I get here? This is R, this is R. Tau. Very good. Somebody has written tau times T times delta S. Right. This is the force. Correct. Right. This is the force. Is this correct? Tau times T times delta S is the force times R. Correct? Times R. Right? And what should I do? I should integrate. So I'll just put this as ds. Right? I need to integrate. Integrate over what? Going one full circle, which means I can put a circle over here. Correct? Yeah. But I know tau t is a constant. I know tau t is a constant, right? So I can take the tau t, right? And I get it to be something like this, right? R times ds. What is R? R is this. S is this, right? So this is ds. This is R. I'm going to roughly calculate what would be this, and this will be nothing but area A equal to half of R times ds. Agreed? Agreed? And therefore I'll get 2A is equal to R times ds. Okay, so I can now take it out and put it as 2. I'm going to call this as dA because this area is small area. All right. So I'll call this as dA, and this 2 times dA. Right. Now, if I sweep over the entire circle, what will I get? I will get nothing but the area enclosed by this. Is it not? Is it not? And I should get this to be 2 times A, which is the area of this circle, times tau times t. From this, I know the area, I know the thickness, right? Can I find out tau? The answer is yes, given that this is the external, this is the twisting moment found out from external torque. Is this clear to you? I have now solved for the relationship between the stress that is produced due to a twisting moment T. So far, okay. And what did I use here? I said, okay, there is a shear flow that is occurring like this, right? And it helped me in terms of taking this tau times T out so that it is easily found out to be this way. So far, okay. That's the beauty of this derivation. So what, sir? Why am I? Why should I be bothered about all this? How will it help me, right? So let me ask you this question. Now, in this derivation, where did I use? Listen to me very carefully. Where did I use the fact that this needs to be a circle? Where did I use? Remember, we started with saying, okay, this could be tau, and then we went ahead, found out whatever it is, right? Did we ever say, okay, it has to be a circle? It is valid only if it is a circle? No, we didn't, right? We started saying circle only because that's something that is familiar to, and therefore we did that. But it need not be a hollow circular section, right? The entire derivation that we did is such that I don't have to bother about whether it is going to be a circular hollow section or some other section. That gives me another power, right? Which means that I can now get into another way of looking at this and saying, okay, if I have something like this, let's say I have something like this is smiling face, okay, by the way, smiling face, yeah. Right? And here, if I have to dodge the shear flow, I can do the same thing here, right? This is the shear flow. And what do I know about this shear flow? What I know is tau times t is a constant, right? Another thing that I can find out is this derivation is also very similar because this r times ds got converted into the area. So if I take any one of these, this is the area that I'm looking at, which means if I sweep completely by 360 degrees, all I am now doing is taking this as area. Are you with me? Which means that whatever I have derived, it is possible for me to use for section that is not circular. That's a beautiful shift that we have been able to get, as long as it is a thin section. So far, okay? So far, okay? For example, I can move a little bit further and think about many other possibilities. Remember, once I find out tau and I have a relationship with t, how do I find out the angle of twist? Anyone? I need one single phrase that can give me an answer. How do I find out angle of twist? One of you. Ayush. Because he asked me that question earlier, so I'm going to ask him back again. Ayush, are you there? I want to find out the angle of twist. I have
Hello,
already
yes, sir.
derived
Am I
this.
audible?
Yeah, right now
Sir,
you are audible. Yeah,
sir, like one method is like we can take the energy and then differentiate it with it. Yes.
fantastic. Yeah,
Yes.
I just have to take strain energy. I know tau is equal to, I know tau is equal to T by 2AT. Is it not? T by 2AT. And this is connected to the shear strain through G times gamma, right? And then I can use this principle in order to find out what would be the strain energy from the total strain energy. I just have to take the derivative with respect to the torsion T in order to find out angle of twist. Remember angle of twist pi by L per unit length, right? And torsion or conjugates when we write down the strain energy in total, right? And therefore it is possible for me to also find out the angle of twist, okay? Angle of twist per unit length,
But
okay?
sir, we'll have to take modulus of that because angle can go both ways, right? So for the strain energy.
Yeah. So you just take the strain energy and appropriately take whatever sign that is necessary.
Yes, sir.
You're right. But the thing is, it's possible for me to find out the twisting moment. Just that I already have stress, it is possible for me to find out strain and therefore strain energy, and therefore from strain energy using the hyperelastic understanding, it is possible for me to write down the relationship between the angle of twist and torque or twisting moment, right? Another thing that is also something that is coming up is like this. You're going to now look at a familiar drawing. Because you guys must have definitely worked on this. I can have a section like this, no? I can have a section like this. How does shear flow in this? That's a question I can easily answer now, is it not? How does it flow? It flows like this. Okay. Okay. Let's say it flows like this. In this, I don't know whether it is flowing like this or not. But I can assume it to be this way. Now, this looks very familiar to you people, correct? This looks very familiar to you people. I hope you must have done definitely something in fluid mechanics. Are you also doing some electrical sciences now? Electrical circuits, fantastic. So this looks very similar to electric circuit. So what would I do? I would say, okay, this is Q1, this is Q2, right? And the torque is the summation of these two. So I can now write 2 times AQ1 plus 2 times AQ2. This is A1, this is A2, should be equal to total torque. I'm not going to derive this, but you understand that this is the way it goes. And remember, this is like a flow, right? This is Q2, this is Q1. What should this be? That's not very difficult for me, right? Because I can easily find out, because this is a flow, and therefore I know how I can relate Q1, Q2, and this, which is, let's say, Q bar, right? I have done this electric circuits a lot, and therefore I can apply this, and it's possible for me to get the relationship between the twisting moment and the shear stress. Here it's a shear flow. All I have to do is divide it by the thickness. I can write this to be 2A1 tau 1 T1 plus 2A2 tau 2 T2, right? Tau 2 T2. You get the picture now. And now I have just transformed the whole thing, just hijacked the whole thing into like solving the electric circuits, right? This is the beauty of having tried out something which is just for a thin, hollow, circular cross section. Then we went to non-circular cross section, and then we also have some composite sections like this. And I can always expand. I can say one more is like this, right? And I can say, okay, there is this. How do I find out? I just have to add one more here saying Q3, Q3, right? And this is Q3. It is possible for me to solve for whatever it is, because I can now say, okay, the entire cross section is going through the same twisting, right? The entire cross section is going through the same twisting. That I can adopt in order to find out what would be the relationship that I'll get as a constraint. Okay. All right, try it out, and it will be easy for you to understand this. Okay. On the other hand, okay, so we get a picture of how shear flow occurs in all these. I can now think of shear flow for a solid cross section as something that is composed of thin ones all through. We did this exercise, and therefore I can now draw it like this. This is the way shear is flowing. It's like a circular flow, right? Whatever is applicable for the circular flow, I can use over here also. Okay, as I go towards the center, it goes to 0. Correct? This is the flow, right? And if I take a rectangular a square cross section, let us say, how would it look like? Okay, it will go like this here, it will go like this here, it will go like this here, it will go like this here. I can complete it and saying, okay, this is how it could be. You know, it will avoid the corners, right? Whether it is the current or the fluid flow, it's a similar thing. And therefore, I can now draw the contours of flow, right? As I go towards the center, it will become more and more circular in nature. This is how I get it, right? And we also derived what could be the stiffness of this. Do you remember? right? That's what we did in the last class. And as I make it larger like this, one of the lengths becomes larger, then it will be something like this, correct? Right? And similarly like this. You can see that more and more this part of it matters less compared to this part, right? As I make it thinner and thinner, I make it very thin, then what am I looking at? I'm looking at the torque related to primarily these stresses that go around like this, correct? Yeah. So far, so good. Is this understanding clear? Okay, I'm just looking at it from flow point of view, right? Now, if I take this and say, okay, it is like this now, tell me what would happen. Intuitively, it's not very difficult for me. I can just say, okay, it's going to go like this. It's going to go like this. Forget about this point, this side, because it is very small. It will have some very minuscule effect on the torque, but this is how the flow could be. Okay. Now, how is it different from here? Not much of difference, because if I take the total torque by integrating these shear flows, I'll get something which will not be different from here as long as this length is the same as this length. Let's say this is B and this is B, this is T, this is T. The torque that I can find out for this will be the same as the torque that I find out for this. You agree so far? Is this concept clear? I can go further and say, oh, okay, I can now take it to be like this. And tell me what happens. Well, what you've done is you've taken this and just folded as a loop like this, right? And therefore, if I have to draw, it will be like this along one periphery or one surface. The other surface, it will go in the opposite direction like this. And the torque or the twisting moment that I find out, the internal torque or the twisting moment that I find out is very similar to this, which means that I can now unfold it and use whatever formula that I have used for this. So far, so good. On the other hand, if I join them, well, this flow can continue, and therefore the flow will be complete compared to not having the flow complete, right? It has to circulate. This has to keep on circulate. So this is a shear flow that I get for this. But if I take the entire thing to be continuous, then the flow is very simple. The flow will be continuing like this. Is it not? And that will be something that I already know, which will be T is equal to 2A tau times T, correct? Which is not the case for this. For this, we already found out that J is equal to 1/3 of B times T cube. Okay. This will be different from this, and you will see that the ratio of these two, this is very high compared to this. This has a negligible stiffness compared to the stiffness that you get over there. So far, so good. Is this clear? Just stretch your mind a little bit. This will be easy for you to comprehend, having done electric circuits and fluid flow, etc., etc. All right, folks. Let me take you to another concept. If this concept is what I was looking for in class quiz, I'm not going to conduct class quiz today, but I'll just give you one more concept. before I start with that concept, please note that there are two additional concepts that I need to introduce in a formal way. One is about deflections of beams, which we have not done so far. The other is what is called a phenomenon of buckling or instability that happens when there are compressive stresses. These two concepts I will introduce most probably tomorrow and day after. But otherwise, I'm going to introduce all special concepts that if you know, you'll be better off as far as somers are concerned. All right? Okay. So let me just introduce the next concept. Yeah.
I have a doubt in the rectangular cross section. We are applying the torque at the center, right? Sir?
Yeah. See, it doesn't matter. If it is not at the center, will the torque be different?
Sir, but like it doesn't make sense that the torque will be in the opposite direction.
Supposing I have like this, I take torque about this point. Will it be different? Moment about that point. Will it be different? Remember, this is a couple. This is a couple, right? Bindu, did you understand? You know something about couples. What is that? Something about couple. Couple means couple of forces. If I have couple of forces like this, I take moment about this or about this or about this or about this, what will I get?
They'll produce the same moment.
Exactly. So the same thing will happen over here also. I can take moment about any point. It does not matter which one is the center. All right. Okay. The flow is like this, is what I've shown.
Yes.
And in the next concept, I will tell you this is not the case when it comes to the other concept. All right. This is clear to you. All right. I'll not take more than 5 minutes as far as the other one is concerned. Any other question? Good question, Bindu. Any other question? Okay. Let me move on to the other concept, which is also a very nice concept, which I alluded to a certain extent earlier, but I'll just go ahead, let you know. For example, I have a beam, and let's say a load is applied. Okay. I'm now going to assume that the cross section is rectangular. Okay. Let's say a long, the height is high compared to the breadth, let us say. So due to this, what will happen? It will create shear, right? I'm not going to draw the bending stresses, but the shear stresses. I'll focus on shear stresses. Okay. How will the shear stresses look like? They look like this, right? It will taper off to small value as it goes to the end here. Similarly here, the value is higher here, but the flow seems to be going from here to here like this. Okay. And this flow is opposing this flow, this shear stress. Okay. This is tau. Okay. And I can, if I multiply by the thickness, which is B, I'll get the flow, Q. Okay. Remember, this Q is not a constant throughout. Okay. It is varying as you move from one point to the other, from the center till the end. Okay. All right. As I make it thinner and thinner, it will become something like this. Correct. I can just use one single arrow and say, okay, this is how it is. This is small, this is large, and this is how it would be. Correct. Let me do it for other sections. Okay. If it is a circular cross section, what will I get? Well, that's very easy. I'll get it to be something like this. This is small here. But if I integrate the total, it will come out to be V, right? That's something I know. Let me go to another section. Okay, let's take I section, that which we did in the class. I section. So what do I get from for I section? I section seems to be, this will be going up like this, correct? Right? And how about this side and this side? It will be like this, tapering off, similar to earlier cases. This will be tapering off, this will be longer, right? In a similar way here, it will be in this direction like this, and in this direction like this. In a way, you can see that it is starting from here and going like this, starting from here and going like this. Are you able to see? There is some kind of flow that I can intuitively get an idea of, right? Let's draw some more. How about T? That's easy for you. Well, sir, this is very simple. All I have to do is go like this, and then it separates into one like this and another flow like this. Okay, simple. Okay. Well, let me complicate it a little bit more. Okay, this is the shear that we are looking at, right? Let me change it to a certain extent. I'll probably chop this off. I'll chop this off and chop this off. How about that? Okay. We call this as C section or channel section. Okay. What would I get? Well, this flow will be very similar, not much of change. It will start from here, go all the way and go to this, right? But there is one point. Where is the centroid here? Centroid is somewhere over here, correct? This is the centroid. So I should actually be applying along this. So far, okay? But if I take the resultant of this, right? This one and this one will cause a twisting, correct? If I take moment about this, I should get that moment, which is a torque, should be equal to 0 ideally. You agree with me? This is an important thing that I want you to get. I have a beam and I am applying a transverse load, right? If the transverse load is applied through this centroid, I'm trying to find out if it will produce any torque at all or not. Okay. Will it produce torque? If I apply like this, will it produce torque? Any guesses? Think about it. If I take moment about this for this, this and this, all are in the same direction. They go only like this, right? Which means that I produce a torque T, right? And this internal forces will produce another twist to the beam. So if I have a channel section and I apply a load through the centroid, mind you, what will happen is it will start to rotate because there is an unbalanced twisting moment that is occurring, right? And this unbalanced twisting moment is going to twist the beam, right? And if you don't want it, what will I do? I need to find out a point. I need to find out a point such that the moment due to this, so this is causing one like this is causing one like this is causing the opposite direction. And I have to match this opposite direction to these and find out what point that is. And that point is called the shear center. And how about the rectangular cross section? It so happens that the centroid and the shear center, so I'm going to call it as C here and SC here, both C and SC are the same. Whereas here, C is different, SC is different. How about an angular L cross section? Well, this is the shear flow, correct? Centroid is somewhere here, right? Centroid is somewhere here. If I apply the shear in this direction, definitely there will be an unbalanced torque that is applied, that is coming about, and it's not desirable to do that. So what would be the best point that I choose as the point of application of this transverse load? Any guesses? One should be opposing compared to the other, correct? What would that be? Definitely not in this region, correct? Right? Because both this and this will produce the same directional torque. So I should go outside. Supposing I go over here, what will happen? This will give me like this. This will give me like this, correct? And similarly, over here, and therefore you can easily conclude that if I take a point over here, this guy will give me something that is twisting like this. This will be giving twisting like this, both same direction. So which point would I choose here? Right? I want you to think about this. Okay. I can take any section and ask the same question. Right? But the fact of the matter is I have a center of the twisting moment that is equal to 0. At this, the twisting moment is 0, and therefore I can, if I apply the transverse load alone, it will retain that particular the orientation of that section throughout the beam. If not, what will happen is this orientation of the cross section will start to twist. Are you with me? Right? And that's how we find out the shear center. Got it? This is another concept that you should know. Where do we apply the transverse load? Okay, is a very important question when it comes to beams, right? Beams of what? Beams of unsymmetric cross section, because we found that if it is an I section, the centroid and the shear center will be the same, right? Because I have one like this, I have one like this, but I have one like this and one like this, which cancel each other. And the center one, I don't have to bother, right? It's the same thing with T section, right? One is like this, the other is like this. So if I take a point which is the centroid, it happens to be the same. So I can apply the shear in this direction, right? So any symmetric cross section, the shear center is going to coincide with the centroid. If not, if it is not a symmetric cross section, then I have to be worried about what it is. For example, if this is a section that is like this, let us say, and I apply, then what would happen? This will be like this, correct? And I have one like this, and therefore if I take about the centroid, this and this will cancel off, this and this will cancel off, and therefore it will remain the same as shear center being the same as the centroid. Okay. So in what direction I apply for this C section is important. Okay. You can think about any other cross section. Supposing I have a Z-like cross section. Okay, the centroid lies over here, right? Find out whether shear center lies over there. Okay. So would this be better if I have to apply the shear in this direction compared to something that is like this, where I have to apply somewhere away from the cross section? These are the questions that we start to ask when it comes to some way offsetting the artificial unbalanced torque that is produced due to the flow of shear that occurs in beams. I just want you to get an idea and be aware that this kind of a thing should happen. Calculations and all those can just follow, and it's not very difficult for you, right? Because you are familiar with free body diagram. Okay, folks. So we learned two concepts today: the flow and how to deal with the thin, hollow cross sections for torsion. The other is thin sections, or it need not be thin sections. How do we now differentiate between application of transverse load at the centroid and the shear center? Okay. Remember, this is very different from whatever we did earlier, where when we applied load like this. Here, I want you to figure out which is the direction that I have to take in order to offset as far as shear center is concerned. Here you will find that there are two directions, one direction upward and the other is y direction. Look at these two direction forces and you get an idea of where the shear centers should lie. Okay. The intersection of these two should be the shear center. Okay. Here also it's the same. Intersection of these two should be the shear center. If you look at this is here, and therefore if I apply load like this on the shear center, it remains the same, right? And if I apply in the other configuration, it should be the same. If I take any other orientation and I apply the load, I should apply on this shear center, because this is an intersection of this and this. So far, so good. I know I've covered the entire stuff in 10 minutes, but I wanted you to get an idea. Time is up. Thank you. Just munch over whatever we discussed today. Okay. Thank you, folks. Have a nice day. Don't get too stressed up due to assignments. Just use some of those things that we discussed